strong winds and heavy seas caused by a fully developed extratropical cyclone. Tropical cyclones and typhoons sometimes dominate the seas with devastating forces. The routine passages are in these sea areas where meteorological phenomena often cause heavy seas. What is expected for navigators to ensure safe and economical voyages in such a precarious natural environment? This shows clouds over Japan from the generation of a low pressure to its disappearance. Let's see how these lows generate and develop. The generation and the development of an extratropical cyclone are greatly affected by air masses in the near-sea areas of Japan. When high pressure stays over a continent or an ocean for a long time, a large homogeneous air concentration may build up. This is called an air mass. There are two air masses affecting the meteorological condition in the near-sea areas of Japan. One is the Siberian air mass, a cold air mass. The other is the North Pacific air mass, a warm air mass. Depending on seasons, the Okhotsk air mass and the Yangtze air mass also affect it. Let's take a look at the generation and development of extratropical cyclones in detail. When air masses with physically different characteristics come into contact with each other, fronts are created in the frontal boundary zone. When a warm air mass is predominant, the warm air mass moves towards the cold air mass and pushes the front forward with a lighter warm air creeping up the frontal boundary of the cold air mass. A front formed in this manner is called a warm front. Conversely, when a cold air mass is predominant, it moves towards a warm air mass, and the cold air mass moves the frontal boundary forward, raising the lighter warm air mass. A front formed in this manner is called a cold front. An extratropical cyclone generates on this front. If the warm air mass in the south of the front moves northward, and the cold air mass in the north of the front moves southward, an updraft occurs due to the contact between warm air and cold air masses. This generates a counterclockwise spiral flow of air growing into an extratropical cyclone. The larger the difference in temperatures between the two air masses in the north and south, the larger the extratropical cyclone. For these reasons, larger extratropical cyclones develop in winter than in summer. These extratropical cyclones generally move northeast, approximately at a speed of 40 kilometers an hour and 10 degrees in longitude a day. The approximate maximum wind speed can be calculated using this equation. For example, if central atmospheric pressure is 1000 hectopascals, the maximum wind speed can be estimated at 15.8 meters per second using this equation of approximation. Extratropical cyclones can be classified into two classes. One is called wind and rain class, by which central atmospheric pressure is 1,000 hectopascals or less and maximum wind speed is 15 meters per second or more. And the other is called stormy wind and rain class, by which atmospheric pressure is 980 hectopascals or less and maximum wind speed is 25 meters per second or more. It can be said that an extratropical cyclone develops when its central atmospheric pressure falls to 1,000 hectopascals or less and decreases at a rate of 10 hectopascals or more per day, with an advancing speed of 50 kilometers per hour or more. We can get data to forecast an extratropical cyclone from surface and upper level weather charts. To understand meteorological phenomena caused by an extratropical cyclone, it's necessary to grasp the three-dimensional conditions of atmospheric air movement within the troposphere up to approximately 12 kilometers from the ground surface. Knowing the weather at the upper level within the troposphere shown in this chart is essential to learn the surface weather. For this purpose, the following upper-level weather charts are produced to analyze data by height. 850 hectopascal contour chart at about 1,500 meter layer, 700 hectopascal contour chart at about 3,000 meter layer, 500 hectopascal contour chart at about 5,500 meter layer, and 300 hectopascal contour chart at about 9,000 meter layer. A surface weather chart is drawn with isobars based on the observations of atmospheric pressures on the ground surface. By contrast, upper-level charts are drawn using contours of parallel altitudes at specific atmospheric pressures with solid lines and isotherms with dotted lines. Ships mainly refer to 500 hectopascals upper-level charts. This is because levels of 500 hectopascals correspond to approximately half the average height of the troposphere, and its atmospheric pressure is about half that of the ground surface. These extratropical cyclones tend to generate in front of a trough in the upper level. When a trough deepens from the day before, a low develops on the surface below. We also need to keep an eye on the movements of upper-level isotherms because movements of upper-level cold air towards the south may cause extratropical cyclones to develop associated with gusts. Special attention should be paid to the movements of isotherms of 500 hectopascals upper-level charts at minus 30 degrees centigrade and minus 36 degrees centigrade in winter and minus 24 degrees centigrade in spring and autumn. As already explained, it's recommended that navigators should use upper-level and surface charts in an optimum combination. Lows generated in a tropical zone are called tropical depressions. In Japan, a tropical depression with a maximum wind speed of 17.2 meters per second or more is called a typhoon. This chart shows the regions where typhoons generate. As you can see, the Eastern Sea area off the Philippine Islands is the birthplace of typhoons where the largest number of typhoons generate. Paths of typhoons generally come in two types: those traveling northwest after birth and those recurving rightwards along the western fringe of the North Pacific Ocean high, then traveling northeast influenced by westerlies. The path of the right turn type is largely dependent on the strength of westerlies and the North Pacific Ocean high. Most typhoons at first tend to advance east, bearing on the North Pacific Ocean high in the 500 hectopascals upper level chart at its right side along 5,820 meters or 5,860 meters contour. Recurving points of typhoons may vary corresponding to the pattern of the ridge of atmospheric pressure of the North Pacific high extending east to west. Let's take a look at a few days of movements of one typical developing extratropical cyclone in the near-sea areas of Japan in detail, referring to related surface charts. In the near-sea areas of Japan, many extratropical lows generate from autumn to spring, and sometimes they develop to levels comparable to typhoons. They are categorized into three patterns corresponding to their origins and ensuing tracks as follows: East China Sea lows, the Japan Sea lows, and twin lows. The East China Sea lows, as shown in these surface charts, originating in the East China Sea or near Taiwan, develop while they proceed northeast when a rigid winter atmospheric pressure pattern with highs in the west and lows in the east begins to deteriorate from the end of winter to early spring, forming troughs and corrugating isobars along the south coast of the Japanese archipelago with a bulging continental high to the southeast. Lows grow particularly rapidly, accompanying very heavy seas towards the northeast along the south coast of Japan, when they move at a speed of 50 to 80 kilometers per hour. When a low in the Sea of Japan, as shown in this surface chart, develops rapidly in a trough over the ocean, like the East China Sea lows from the end of winter to early spring, as highs in the west and lows in the east, the winter atmospheric pressure pattern deteriorates, and most areas of Japan are covered by warm air from southerly winds towards this low. If a high exists on the south side of the Japanese coast, atmospheric temperature will rise, causing strong southerly gusts. This is called a vernal storm with high waves. However, the supply of warm air does not last long, and temperature drops abruptly, and a winter pattern, accompanied by a cold north wind, returns after the cold front passes. In April 1994, the distress of the 4,769-ton White Fuji was caused under such weather conditions. Twin lows, as shown in this surface chart, appear from November to March, one in the north and the other in the south of the Japanese archipelago, and proceed to the east side by side, developing further off the Sanriku coast when they coalesce into one low. At this time, a strong monsoon would follow behind this low with heavy seas. After the low has moved east under the influence of these three weather phenomena, A typical pressure pattern of highs in the west and lows in the east is often established. Let's take a look at such a typical pressure configuration. A typical winter pressure configuration of highs in the west and lows in the east, as shown in this surface chart, appears from November to March. When the continental high extends to cover Japan and a developed low exists in the northeast area of Japan in the North Pacific, the winter monsoon grows stronger and lasts longer. The winter monsoon blows so strong because the pressure gradient becomes larger when both the high in the west and the low in the east develop at the same time. In the areas east of Nojimasaki of Japan, marine casualties involving large ships have often occurred due to high waves caused by the winter monsoon, which lasts for a long time with long fetches over the sea surface. In addition, as the southern tip of the upper cold air passes this sea area, causing turbulent airflows due to convection caused by the big difference in temperatures between cold air of the upper layer and the warm surface layer over Kuroshio Current, wave heights increase. This is why unusually high waves generate over a wide area. This high wave area extends 30 to 37 degrees north in latitude and 140 to 160 degrees east in longitude. As this high wave area appears in the southwest quadrant, far from the center of the low, it's necessary to know the movements of upper layer cold air from the isotherms of 500 hectopascal upper level charts. Attention should also be paid to the secondary and tertiary cold front formed by cold air from the Siberia cold air mass in waves which cause areas with high waves. Numerous major marine casualties have occurred in this area. The Bolivar Maru, 50,000 tons, on 5th of January 1966. The Sofiapi, on the 6th of February 1970. The Antonio de Mades, 16,000 tons, on the 7th of February 1970. On the 9th of February of the same year, the California Maru in the same area. Although its effect is smaller and local compared to cases explained previously, attention should also be paid to streaks of convective cloud over the Sea of Japan. When the winter monsoon begins to blow again, after the winter high pressure pattern in the west and lows in the east deteriorate, with isobars over the Sea of Japan moving towards the continent, the northwest monsoon revives with northeast winds from Primorskij and northwest winds from the Changbai mountain range in the northern Korean peninsula, converging in the southern area of the Sea of Japan. Let's take a look at some related photos. Why does such a phenomenon occur? Winter monsoon patterns are shown on this chart. Numerous eddy currents are created within the belt like convection cloud formed along the convergence line if cold air current prevails in the upper layer. Inside, such eddy currents become very dangerous due to chopping seas built up by the superimposition of two waves coming from different directions. The cargo ship Maritime Gardenia, 7,027 tons, container ship View Africa, 6,944 tons, and one squid fishing boat, 45 tons, were in distress. When navigating in the open ocean, it's important for a ship to avoid extensive high wave areas in extratropical cyclones for cost-effective operations. For this purpose, navigators are recommended to take the weather routing into consideration. Weather routing is a technology to select an optimum route for a ship using a computer simulation based on the forecasted ocean environments, taking ship speed and seaworthiness in predicted ocean waves into consideration. Weather routing provides a recommended optimum route from point of departure to point of destination of the ship based on the results of a computer simulation. The ocean environmental conditions, such as wind and waves, which affect the navigation of a ship, are predicted by a computer calculation every day on the grid points covering the whole area of the ocean up to about 10 days ahead. These charts are 24-hour, 48-hour, 72-hour and 96-hour forecast data on sea winds. These are 24-hour, 48-hour, 72-hour and 96-hour ocean wave forecast data. An estimation of ship speed in the ocean waves is generally deduced statistically from an analysis of actual data in a ship's logbook. The seaworthiness of a ship is also estimated through calculations and used in a simulation for optimum routing. Deliberate reduction of speed by reducing propeller revolutions will be necessary when the frequency of shipping seas at the bow and slamming exceeds critical values, or the engine becomes torque-rich. These critical values are also included in the calculation. These curves were obtained from an analysis of actual data on ships' logbooks. From this chart, ship speed in the ocean waves corresponding to a specific height of waves and encounter angle to the waves at specific engine revolutions can be obtained. For example, if a ship proceeding in the following seas with a wave height of 11 meters at 79 RPM propeller revolutions, ship speed may be maintained at 19 knots. However, at an encounter wave angle of 90 degrees, engine reaches torque-rich at a wave height of 9 meters, and when the encounter wave angle is 60 degrees, the engine reaches torque-rich at a wave height of 7.5 meters. In these torque-rich cases, it will be necessary to reduce engine speed, and when proceeding in head seas, it will be necessary to reduce propeller revolutions when wave height becomes 6 meters to avoid the risk of shipping seas at the bow. Thus, if weather and sea conditions can be predicted, and ship speed in ocean waves and other necessary factors can be obtained, an optimum route is calculated using a simulation. The optimum route for the shortest voyage time is calculated using the isochrone method. An isochrone represents the locus of the outer limit points reachable within a specific time from one departure point. Imagine ripples spreading on the surface of water when you throw a pebble into a pond. The outermost ring of ripples corresponds to an isochrone. Next, we will explain how to calculate the minimum time route by using the isochrone method. Let a ship sail from the original departure point, x0, following various ships' headings on both sides of the original Great Circle route to the destination. In this case, the ship is navigated with speed deduced from the forecasted wind, wave, and ocean current data, and compute respective arrival points, x1, of the ship at 24 hours after the departure time. The set of x1 represents isochrone. Next, let the ship sail from each point, x1, with various ships' headings, and compute the arrival points 48 hours after the departure time. Here, draw Great Circle routes from the original departure point, x0, radially on both sides of the original Great Circle route. Then select the most distant point in each area between neighboring two great circles, and define these most distant points as x2. The set of x2 corresponds to the isochrone at 2 days after the departure time. At this moment, the departure point x1, from which the ship arrived at x2, should be memorized. Repeat this procedure until the ship approaches the destination enough and obtain the final isochrone xn. Then make final ship run from each xn to the destination and pick out the point xn which has minimum sailing time to the destination. To determine the minimum time route, find the departure point on the previous isochrone from which the ship arrived at the point xn. Then find the departure point on the second previous isochrone. Repeating this tracing procedure back to the original departure point x0, the minimum time route from x0 to the destination can be obtained. This chart represents calculated daily isochrones from San Francisco to Tokyo to obtain the minimum time route. As shown in this chart, since high head sea areas can be easily identified from the pattern of the isochrones, this isochrone method is very useful to determine the optimum routes. The term minimum time route signifies a route that enables a ship to reach a given destination in the least time, taking her state of seaworthiness into account, and does not necessarily preclude passing through some areas in which the weather is heavy. It may be necessary, however, to ride out boisterous weather depending on where it's encountered. This simulation was made at the time of the ship's departure. However, the optimum route should be recalculated when wind and wave forecasts are updated during a voyage to respond to the change of wind and wave conditions which was unexpected at the departure time. The calculated optimum route is provided to the shipmaster as a recommended route. When navigation in a tropical depression or a typhoon is inescapable, it's essential to collect information from meteorological organizations to take the necessary countermeasures. In addition, Bayes-Ballott's law is also useful to deduce the center of a storm area. The law says that the center of a depression lies 15 to 30 degrees left forward from a left arm raised horizontally to the side when a person stands with his back against the wind in the northern hemisphere. This law can be applied to an extratropical cyclone. It's necessary to know the relative position of a ship to the subject tropical depression or typhoon to minimize its effects. When a typhoon is moving north and wind direction observed on board changes clockwise, the ship is in the right semicircle of a typhoon. In contrast, if the wind direction changes to counterclockwise, the ship is in the left semicircle of a typhoon. The rate of change of wind direction is larger when the distance between the ship and the typhoon is smaller. Conversely, the change becomes smaller when the distance increases. A large change foretells abrupt and drastic directional change of wind direction. Most ports and harbors located along the southern coast of Japan and not sheltered to the south become dangerous due to strong southerly winds blowing towards the land when a typhoon passes to the west while proceeding north. The semicircle to the right of the center line of the typhoon's path is called the critical semicircle, where original winds of the typhoon are enhanced by same directional prime mover air current. If a ship is in this semicircle, it will endure a pressing wind towards the center. When a typhoon is in the far southern ocean area, its storm area is almost circular. It not only expands the storm area evenly, but also tends to develop an east semicircle prominently as it approaches the near sea area of Japan. The reason why the right semicircle is called the critical semicircle lies in this phenomenon, particularly if the southeast quadrant of the typhoon becomes a strong wind and high wave area. As you can see in this ocean wave chart, a high wave area lies in the southeastern quadrant. On the other hand, the reason why the left semicircle of the advancing path of the typhoon is called a navigable semicircle stems from weakening typhoon winds due to the adverse prime mover current of the typhoon. And when the ship is in the right semicircle, the wind presses the ship behind the typhoon. Nonetheless, even in a navigable semicircle, as it accompanies a storm area, proper caution is necessary. Therefore, it is advised that the course is maintained to keep the wind at the starboard bow when in a critical semicircle, and at the starboard quarter when in left semicircle to turn away from the typhoon. Today we can easily receive various maritime meteorological information such as surface charts, upper-level charts, ocean wave chart, and photos taken by meteorological satellites broadcast by the Meteorological Agency. We should bear in mind that among this information is a lot of data transmitted from ships at sea based on their own weather observations. To supply these ships with more precise maritime meteorological information, weather observations and transmissions by ships at sea remain essential. It's important for seafarers not only to endeavour to acquire the necessary knowledge to make best use of this information, but also to have safe and cost-effective shipping operations.